Hello, my name is Patrick Simmons, and I am an applications engineer supporting position sensing products. In this video, I will provide information to help guide you in your magnet selection with Texas Instruments Magnetic Sense Simulator tool, also known as TIMS. Upon starting a design, you will be prompted to choose from 6 basic shapes. For linear movement, axial cylinders and bar magnets are popular choices, while diametric cylinders and ring magnets are popular for angle encoding. Half of the shapes only permit 2 poles, including one north indicated by red and one south indicated by blue. However, for bar magnets, you can create a lateral array with increments of 2 for the poles. As for the rings and axial rings, the pole count corresponds to the outer poles, which is why ring increments in multiples of 2, while axial ring increments in multiples of 4 above the default 2-pole count. If you find you have not selected the appropriate shape or you want to experiment with different shapes, you can modify your selection once you have reached the main design screen. By clicking the magnet shape drop-down menu, you can change to any of the shapes shown in the prior design stage, just like I'm switching from cylinder to bar right now. Magnet shape is just one of many variables that influences the field observed from a magnet. Other variables include material, dimensions, and relative location with respect to the sensing location. There are a few common classes of magnet materials. Within each of those classes of materials, there are different grades. These grades correspond to standardized values for remanence, temperature coefficient, and coercivity. Larger remanence corresponds to a stronger magnet. Here is a chart showing remanence values for different magnets. Many of these are listed in the tool, but some are not. For instances where your magnet is not listed in TIMS or the magnet datasheet, you can use the custom material to tailor the magnet property values to your needs. Temperature coefficient describes how magnet strength changes with temperature. After specifying the magnet material properties, you can then set the size of the magnet. Larger magnets will have stronger fields. After specifying the size, you can then set the magnet location, orientation, and its range of motion relative to a global origin. When specifying the magnet position, remember that the origin for the magnet is at the magnet center. X, Y, and Z angle are all relative to the magnet origin, with rotations performed in X, Y, Z order. The magnet origin moves to the specified final position relative to the global environment origin indicated by the intersection of the red x-axis and the green y-axis. To impart some intuition on how you might need to orient your magnet, how about an example of a cylindrical magnet moving linearly above our sensor from the perspective of the magnet? If we focus on a single flux line, we can see that it can be discretized into smaller vectors. Subsequently, by focusing on the vertical portion of the flux vector, we can extrapolate the vertical component at different locations from the magnet. Expanding the initial generalization, we can also extrapolate how weaker flux lines contribute to flux measurements at further locations. That shows how to select a magnet in TIMS. To learn more about TIMS and position sensing related topics, please see the relevant collateral linked here. To get started with designing your magnet sensing solution, please visit webbench.ti.com/TIMS.